Okay. Do y'all see my camera on or not?
No, sir.
You don't see it?
I don't see it.
How about now?
I see it now.
Okay. All right. This is Durwood King with Sampson Community College, and this is a ELC 111 Intro to Electricity. And this is we're going to be covering Chapter 3 today on series circuits. We'll do a little review on Ohm's Law from Chapter 2, and then we'll move forward in Chapter 3 for series circuits. So thank you for joining. If you have any questions, if you're watching recording, you can call, text, or either ask questions when you're here, in person. But I'm available. You can get it with me pretty much any day, and I'm flexible on hours if you have questions when you're working on your worksheet. So those of you that haven't started the Chapter 2 worksheet on Ohm's Law, there are quite a few calculations in there, and go ahead and try to work on that and try to stay up on your worksheets. And the worksheet for Chapter 3, I don't have it in Moodle yet, but I will this weekend, probably sometime tomorrow. But just check it over the weekend, and when you see it, you go ahead and start working on it. And we're going to go over some of those items today together. So one thing we're going to do first before we get into Chapter 3, we're going to take a look at let me get the right thing queued up here. There. Now, do y'all see my webcam in a large view now?
Yeah.
You see it like full screen?
Yes, sir.
Okay. Now, how many of you know what this is?
Heating element.
It's a heater element. It is. This is what goes in your water heater at home. How many of you have a traditional water heater at home?
Yeah, I do.
Most people do. They got them now that are called tankless, to where it actually heats the water as it goes through them. And those, I'm not sure whether they're using, they may be using a different type of heating technology than this. But I'm going to show you something about this heater element here, and we're going to use this as an example of how to understand more about the heater element using Ohm's Law, and then we're going to go into Chapter 3. Okay. Now, one thing different between the heater element and the light bulb is this: they both give off heat. We know that a light bulb gets hot if you touch it, right? It's got resistance in it. We know that now. And but the light bulb, here's the characteristic about it as far as the resistance goes. The resistance that you check of this bulb when it's cold is going to be fairly low. It may be around 16, 17 ohms or 20 or something, depending on the wattage of it. Somewhere in the range of 11 to 25 ohms, in that range, depending on the wattage. That's when it's cold. And when you power it up and it burns, it's going to be, the resistance goes up a lot higher. You're finding that out in your calculations on the labs that you're doing here, that some of y'all did Tuesday. So it has a cold resistance, and then it has a hot resistance that the hot resistance can only be calculated once you measure the voltage with it on and measure the current that goes through it, using the ammeter, the current meter. And then you're using the volts divided by the amps to calculate the hot resistance, right? Now, so that's a characteristic about the bulb. The heater element is different in that the resistance of this heater element does not go up and down. The cold resistance is basically the same as the hot resistance with a heater element. So it's a lot more stable, and it's a better thing to use in learning Ohm's Law. And we're going to just show you a great example of how that works. And I'm gonna get the camera over like this. Now, when you have a heater element, there's some information stamped on it. When I touched that camera, it cut off now. So when I show you this information here written on it, what do y'all see there? The information written right on there.
The wattage and the voltage.
Right. If y'all will jot that down, what do you see? Is it good and clear?
3,500 watts and 240 volts.
Good. Jot that down. Benjamin, do you see that? Can you hear me?
Yes, sir. I see it.
Okay, Roger, do you see it nice and clear?
Yeah.
Okay, great. Jot those numbers down, and I got a couple of questions for you. Let's use Ohm's law, and I would like for you to tell me how much current, how many amps really should flow through this heater element when it's hot. So we're given the wattage and we're given the voltage. Now, I'm going to put up there at the same time, I'm going to put the chart, the Ohm's law chart. And so we're going to try doing this at the same time here. You can see the information stamped on there. Now, what formula can I use to get the amp draw on that heater element? You can actually go to one of the triangles if you want to, or you can go to the pie chart. The pie chart actually is where the triangles come from. And we're looking for current. Now, current is represented by what letter? You know, we measure current in amps. And what letter do we use to represent current? You know, they don't have the A for amps, but they have a what? What's the letter for current? Do y'all see the Ohm's law chart on the screen? Do you see the chart on the screen?
Yeah.
You do? You see the pie chart and then the triangles?
Yeah, I was just getting my stuff out.
Okay. I'm just double checking because I know when we do Zoom, you just never know when something could go wrong. But y'all get your calculators out or your phones. You know, you got a calculator on the phone, and work with me through this. And I would like for you to tell me, how do I calculate the amp draw for that heater element right there? Now, the wattage, the 3,500 watts, that's represented by what letter in the formulas? You know, we measure power in watts, but what letter is it in the formula? What letter do we use for power?
P, I believe.
P.
P.
That's right. P is power. And the unit that the unit of measure for power is the watt. So we measure power in watts. And then the 240 volt, voltage is a unit, but what letter do we use to represent voltage in the formulas?
E.
E. E. Now E stands for electromotive force, which is what voltage is. So we measure electromotive force in volts.
So it'd be 1.4 or 1.5 if round to the 10th.
Which formula did you use?
P over E equals I.
P over E equals I. Right. P over E equals I. And then what number did you get?
1.4583333.
1 point something?
Yep, 1.4583.
No, there's something wrong with the calculation there. 3,500 divided by 240.
I got 14.58.
Oh, 3,500. I missed a 0.
Yeah, 3,500.
That is 14.583.
14.58. And that's going to be how many? Is that what unit is that? 14.58 what?
Amps.
Amps, exactly. Does everybody agree with that?
Yes.
How about Benjamin? Do you agree with that?
Yes, sir.
Okay, is that the same number you got?
Yeah.
Now, so that's correct. That's the right number of amps. Okay, now I want to ask you, what should the resistance be? How many ohms should this heater element measure? How many ohms should it measure? Now, there's a couple of ways you can go about doing that. And if you look, do you see my mouse moving around on the screen? Can you see my mouse moving around?
Yes, sir.
Yes.
Now, you tell me which formula would you use to calculate resistance in ohms?
E over I equals R.
Right. E over I equals R. And basically where I'm putting my mouse at, if you cover up the R down there in that triangle, if you cover that up, that's the one that you're calculating for or solving for. When you cover up R, what's left is E over I, and that's correct. So you have E and you have I, right? So what do you come up with now? So what does E equal?
E equals your voltage.
Okay, which is
240 volts.
240 volts. Okay, and then what's I?
I would be 14.58 amps.
That's right. Now, so how many ohms should we have?
16.46.
Okay, now, so I'm gonna turn this, does everybody agree with that?
Yes, sir.
You took the 240 volt divided by the 14.58 amps, and it gave you 16 what?
0.46.
And 16.46 what? What unit is that?
Ohms.
In ohms, exactly. Now, so do you see my camera in large now?
Yes.
So now what we're going to do is we're going to take the two terminals on the heater element and we're going to measure those with an ohm meter. Okay. When you do it, you want to make sure that the screw terminals, that you actually have the wires off of them. So if this is actually in a water heater, you would want to make sure that you cut the breaker off, and then you come to this here and you check voltage. You measure voltage and make sure that there's no voltage there. You would make sure that the meter, you would check your meter on a known live circuit to make sure the meter is functional, and then you would come up here while it's still wired and checking volts. You would check voltage directly across the heater element like that with the wires there, and make sure that it's dead, that the breaker is in fact off. And then you would remove the wires, both wires from the heater element, and then switch your meter to ohms. So we're going to put it on ohms now. And so which setting do I go to for ohms?
The omega sign.
The omega, exactly. Right. Okay. And I'm gonna reposition the webcam, so it's gonna be rocky here just for a second. This camera's nice. It's got a flexible gooseneck on, and it works out really nice. So right now, the ohm meter is telling us, it says OL. OL means over limit, and with the leads apart, it can't calculate the resistance because it doesn't have anything to even calculate with right now. There's no circuit. I don't have it touching anything. So I have an open circuit. It's going to read over limit. The limit would be whatever the maximum resistance of that range is. And it doesn't tell me on here what the maximum of the range is. I have to get the little handbook out for it to know. But some meters have a limit of just 1,000 ohms. Like I'll show you this little meter over here. You see this one? This is a T5 1000. It's the fluke meter that has the fork for measuring amps instead of the open clamp like that. I mean the closed clamp like that. You check amps inside here or in this open fork here. Now with the T5, it's got its advantages to it. It's slimline. The test leads actually fit into the back of it nice and neat. It's very compact. But on the resistance reading, what do you see here?
1 kilo ohm.
1 kilo ohm, and the K means what?
1,000.
So the limit of this meter is it won't read any higher than 1,000 ohms.
Okay.
If you go above 1,000 ohms, very far above it, it may go a little bit above it. It ain't gonna go far. If you get around 1,500 ohms, 2,000 and up, it's gonna say OL. Okay, so it has that limitation to it. So these meters, this one is very limited on resistance range. It won't go high in kilo ohms and it won't read any mega ohms. So this is just for very limited amount of things you can do with it. So the OL means over the limit of the 1K in this case. All right. So it means that OL, you could get an OL if you read something that say 1,500 ohms, it would say OL. But it doesn't mean, in other words, this meter really can't, some people think that OL means open leg, but it doesn't mean open leg. It seems like it might mean open leg, but it really means over limit of the range of that setting on this particular meter. That means it's above 1K ohm, okay? So there are devices that would read higher than that when you're checking coils on relays and you're checking resistors in circuits and things like that. They can be well above that and nothing be wrong with them. But this meter, if you check a device that has more resistance than 1,000 ohms, this meter is going to tell you, oh, well, and you may say that particular device is bad when it's not. So you got to go up to a meter that can read, has a higher range, okay? This meter here, I'm on the ohms. And what do you see up here for OL? What do you see there, the letter?
M.
And it's the uppercase M. And what does the uppercase M mean?
Mega.
Means what?
I was just guessing.
What did you say it meant?
Mega, I'm guessing.
Mega. And what does mega mean? I'll grab a sheet. Does anybody remember what mega means? The prefix, the large M in front of the ohms, it means mega ohms. And so let me go to a handout that I put in Moodle for y'all, and I think I probably gave you one in person too. Let's go. Let me pull up. And I'm going to resync it here. So I'm switching screens right now. Now, do y'all see the metric prefix sheet on the screen there?
Yeah.
Yeah.
Now, this sheet, let me just kind of clarify something here. That column that says short scale is what we use in the United States, and most places in the world use short scale metric prefixes. Long scale is only used in certain areas of Europe. And I don't know what areas, but when I Googled it, I mean, that's what it just said, that certain areas of Europe use this, but most of the world is using short scale. So here we have the large M, and it means, like you said, Roger, mega. And then in a number terms, what does it mean?
Million.
A million. So it means a million ohms. So one M, if it's a big M, 1 mega ohm means 1 million ohms. And then the K is kilo. And you said that K means 1,000. That's true. So 1 K ohm is 1,000 ohm. 1 M, 1 mega ohm is 1 million ohms. So the most popular prefixes that we use in an electrical field would be mega and kilo and milli. The lowercase m is milli, and that means 1,000th of something. So a milliamp would be 1,000th of an amp. Okay, and those are the three most popular ones. There are other ones. The micro, nano, pico are used in measuring capacitors, very small amounts of capacitance in capacitors. And then with flash drives, you have flash drives that, it's so many gigabytes on a flash drive, or when you're paying for your data on your cell phone plan, you're talking in gigabytes. And a giga would be a billion of something. So if it's a gigabyte, it would be a billion bytes of data. And then hard drives are getting very large in terabytes in hard drive size, external hard drives, and a terabyte T would be a trillion bytes of data. So a 1 and 12 zeros. And then, so anyway, so this is a handy chart to go by. And so with that being said, this meter here can read much higher than cheaper meters. It can go up into the millions of ohms, okay? And it says OL now because there's nothing hooked to it. There's no wires. But if I connect it to a device that has a high resistance, it will read up into the millions, okay? Which is, so keep that in mind when you're using a meter and when you go to buy a meter. So if any of you go to buy a meter, always remember that whether you're reading ohms or volts or amps, look at the specifications on the meter and realize what the limits are. Here, the limits here for voltage would be 1,000 volts DC or 750 volts AC. Y'all see that? So it's actually telling you on this meter, you can't read any higher than 750 volts AC or 1,000 DC. On amps, this actually has a hardwired amp connections there to check amps with a probe. And I'll show you how to do that in a little bit. But it can read up to 10 amps going directly through the meter through this jack, or 300 milliamps through that jack. So that's telling you all of your limitations of the meter. Okay. So getting back to, we're going to see, is your calculation, does it match what we see with the heater element? So look, I'm taking the heater element itself. I'm going to position it so that I can read put the probes right there on the screws on the heater element. Let you see what I'm doing here. So I'm reading right here like that. And let's position it where you can see the glare. I'm going to get rid of the glare. This is a challenge of trying to teach online, is getting things right for the camera. So I'm just coming directly, and also look, before you check the resistance of it, put the test leads together. And you see it says 0.1, or actually that's great right there. It's got way less than 1 ohm on the test lead resistance. See that? So 0.1 is actually the resistance of my test leads, okay? You can subtract that from this reading and get an exact reading of the heater element. So let's go now to the screws on the element. And what are we reading? How many ohms do we have here, guys?
15.7.
15.7 ohms. And you calculated 16.58?
46.
16.46. That's pretty close, isn't it?
Yeah.
So what I'm getting at here is this. This heater element, your calculation that you did, using that data right there directly on the heater element, it allowed you to actually calculate a resistance that's consistent even when it's cold or hot. So heater elements can be calculated directly right off of that as far as how many ohms they should read. So the reason for me showing you that is, if you're troubleshooting one at home, you know, you would naturally go to it, and if your water heater is not really putting out properly, you know, you would go to it and you would measure, even though you would measure voltage, okay, you would be putting on volts, AC volts, as a matter of fact, you know, and you'd go to it and measure the voltage. And let's say if you went to it and it did read 240 volts like it's supposed to, or somewhere between 208 and 240, and the voltage was actually there, but yet the heater element was not giving you any hot water. So by having voltage there, you would know that your thermostat's fine. There's nothing wrong electrically with the water heater. You got power going to the element, but it's just not producing heat. So at that point, you know, once you see that there's voltage there, the second step would be to put this on amps. And then one of the wires, you know, coming off of that, put the amp clamp around one of the wires, one only, while there's voltage there. And see, do you get any amp draw? Do you see any amps being drawn? And if this element is completely burned into on the inside, if it's a complete open circuit, you're not going to read any amps there at all. Zero amps, but you would read voltage. So that's your symptom, is if the element's burned completely into, you would read voltage coming from the thermostat into here, but it wouldn't draw any, there would be no current flow through it, because you had actually a broken element on the inside, that the element was actually an open circuit. So then if you want to prove that it is an open circuit, you shut the breaker off, make sure that it's dead here, remove the wires, and then put it on ohms, check the ohms like we just did, and see, does it match your calculation. So, you know, the Ohm's law allows you to calculate the resistance of this and compare the calculation to the real number, to the actual number, and see, does it match. And it's not going to match if it's burned open. It's going to be, you know, it's going to be way off. It'll be an OL or be extremely high. And then you would know for sure, you just need to go to Lowe's and get one of these, you know. And when you get one, of course, get an exact match on watts and volts. Get an exact match. Does any questions? Any questions, guys?
No, sir.
No questions. Okay. Benjamin, are you okay with everything?
Yes, sir.
Okay, great. And by the way, when I say a thermostat that's controlling this, I can show you just briefly something that you'll learn in motor controls about schematics. I'm going to draw that basic circuit there. So you see my pad here. I got 240 volt here. I've got an AC power source here, and it's going to come out here with an L1 hot leg and then an L2 hot leg. Can everybody see my pad good?
Yes, sir.
Now, here would be a basic water heater that has, if you have a half size, one of those short water heaters with only one element in there. I'm just going to draw that so just for simplicity. You come out of here, and it would actually be now here I have a circuit breaker symbol. You know, that's something that's coming up that you hadn't seen yet, but it's coming up. That's a circuit breaker symbol, and it means that both of those legs have a circuit breaker in there. Let me show you what one would look like. So it will look like this. It's called a double pole. Now, when this breaker goes in the panel, those of you that are taking residential, you know what this is already. You hadn't wired the double pole yet, but you're going to pretty soon. But these two clips here, they snap onto a bus bar in the breaker panel, and it snaps in, and then the power runs through these symbols here that have a curve on them. That's a you know, a magnetic type breaker. And then you connect your wires to these lugs right here, and then you would go out when you leave here. It would go, you know, when you leave here, this is the panel, then it would go to your water heater circuit. So that's a typical double pole breaker. And a 30 amp is what you're going to be using most of the time on a water heater. Now, so we leave there, and then you go out to the water heater itself. And when you get there, you go into a normally closed thermostat. And that senses heat. When I cover that up, it's nothing but a normally closed switch that's closed under normal circumstances. When you put that symbol there, that little step symbol, that means that it's a thermal sensor. It senses heat. And when it senses heat, the hotter it gets in wherever this thing is, this step actually stretches. So it elongates and stretches, and when it does, is it makes the switch actually go up and open. So when you first turn the water heater on, the water is cold in there naturally. And as power runs through the element, let's put the element in there. We come over here, and come straight down, and we're going to draw a resistor symbol. Now, this resistor symbol is the heater element itself. And that would be our 3,500 watt, 240 volt rated heater element. Okay. And so when you start out, the water is going to be cold in the water heater, right? and power is going to run through here through a normally closed thermostat, and it's going to circulate around. And then this is going to get hot, and then you're going to eventually, the temperature of the water is going to build up. And when it does, that sensor, the thermal sensor, is actually going to spread, and it's going to cause that contact to raise and open. So at that point, here's what you would have. When it opens, it looks like this. You see that? So when it raises, it's like a drawbridge opening up at the beach. How many of you go to Wilmington and you cross the bridge, the drawbridge? You know, a drawbridge can open and close. So this is like a drawbridge. And when it's down, you can cross, and when it's up, you can't. You know, there's a boat going through, right? So here, this is called normally closed NC. Normally closed thermostat. Now, when it's open, it's still a normally closed, but it's normally closed held open right now. And that'd be NCHO, normally closed held open. It's held open because the thermal has sensed heat. It's still a normally closed, but it's being held open. Everybody got that? This is for motor controls that you'll learn in January. But I'm showing you that so you can understand the heater element itself and what actually runs it. So it's run completely off of that one contact. And as it gets hot enough, it pops open like this. And then as you use water, take a shower and you wash clothes with hot water, then the water begins to cool down because more cold water runs in through the water heater, you know, to you. And as it cools down in there, what happens here? What happens to this? Everybody with me?
Would it open?
Well, right now it's open when it's hot. When it builds up and it gets hot enough to a set point, you know, you may have it set to 120 degrees Fahrenheit or whatever the set point is on it. When it gets to that set point, it opens, right? But as you use water and more cold water goes into the heater into the water heater, you know, then this is going to cool down, right?
Yeah.
So when it cools down, what happens? What happens to this?
It closes.
It's gonna lower the drawbridge. It's gonna close, and then power's gonna flow again through the heater element, and it's gonna try to build up heat in there again.
Yeah, to heat the water.
Right. That's not a student there. Okay. So yeah, so it's run completely based on if you're at the 120 degrees Fahrenheit or whatever you got it set for. If you are, it opens, and if you're below it, it closes, and it lets you heat. So that's how it regulates. And there'll be a dial setting on this thing. There'll be like a dial, you know, a pointer.
Yeah.
That you can adjust possibly with a screwdriver. You know, you may go in there with a little small control screwdriver like that and turn and rotate, and there'll be some numbers on that dial to be able to set the temperature. So if you want hotter water than what you're getting, you can go in there and maybe turn it up a little bit with a screwdriver, okay? Anyhow, does it make sense what you're seeing here?
Yes, sir.
So what y'all calculated was this. You calculated that as far as the amps goes, it was 14.58 amps. And then 16 what on ohms?
16.46 ohms.
Ohms. So when you go to troubleshoot this, you would be looking for 14.58 amps. Now look at here. If I take the amp clamp and I get around one wire here, one wire, that one or that one, don't matter which one. I'm gonna put around one wire, and if I don't get somewhere close to that 14.58 on here when I check amps, then there's something's wrong, okay? Then you go cut the breaker off. And then you go measure again across here and make sure there's no voltage. It is dead, volt-wise. And if it's dead, when you check volts, remove the wires. You know, you got the screw terminals that are right here. The screw terminals that are there are, right here. You would take the wires completely off of it. I'm gonna put X's there. You would disconnect it, and then you would check the resistance, the ohms, you know, like we did a while ago, and see are you getting close to that. If you know, and if you're not, and then it's definitely you just go get another one of these, okay? And again, you know, make sure that the ratings are the same. You don't want to vary. You don't want to go lower. Don't want to go higher, okay? If you go higher, your actually wire size might not be big enough, and you can have a fire hazard. You know, if you go to a much higher wattage, then here's what's going to happen. It's going to try to draw more amps than that. Your wire size and breaker size are not going to be able to handle that. So it'll probably end up tripping the breaker. You know, if you exceed this. Now, one thing I'll add before we click on to chapter 3 is this. I see Victor trying to get in. Hey, Victor, how you doing? I'll add this one more thing about this heater element now. This thing is rated, it will consume 3,500 watts of power if you put 240 volts on it. Now look at here, I'm gonna rotate it around, and what do you see now? Alternate rating. Alternate rating would be this at your house. If your house doesn't have 240 going into it from the outside, like some houses don't, it could be, the maximum would be this. And actually at my house, it's about 249 volts at my house coming in from the power company. It's almost 250 at my house. Now, here at the school, in our shop, we don't have 240 in there, we have 208. 208 volts. Now that would be the range of the heater element, would be between 208 volt and 240. And it gives you the low rating there. So if you apply 208 to it here, then what's the wattage consumption?
2,500.
Right, 2,500 watts. So it draws 1,000 less watts at 208. You know, 2,500 watts versus 3,500 watts. That's a big difference with a small amount of voltage difference. And you're going to find out why is there such a jump on wattage when there's not such a jump on the voltage. And you're going to get into that with Ohm's law. You're going to see it in your worksheet. Your worksheet is going to reveal it from chapter 2. If you haven't noticed it already, it does reveal that when the resistance of a device stays the same, and it will in this case, when it stays the same, and you increase the voltage going to a heater element or resistor or load device, when you go up on the volts, then the wattage consumption is going to go up, but it's going to go up in a greater proportion because of the way, and I will have to get into that on a particular example. Let's say you can even use this to actually see that. So right now, your numbers agree, and they say that the resistance will be like 16.46 ohms. Now, let's actually drop the voltage here to 208. So if we drop it to 208 volt, and we have, let's say for instance, the same exact heater element, how many amps would it draw at 208? And what formula will we use to calculate that?
What are you trying to find out again?
I wanted to know what is the amps going to be. I want to be at 208 volt. How many amps? How many amps? You see my pad there?
Not clearly.
Not clearly.
Hmm.
Let me draw it. Let me draw it with a pen instead of a pencil.
So your voltage is 208 and your wattage is what?
That clear now?
Yeah. What is the watts?
We don't know what the watts is going to be. That we're going to calculate that. Because look, the wattage is going to drop. I want to know what the amps is at 208 volt for this heater element. But you can't use that wattage because the wattage changes when you drop the volts. So if
So we only know the voltage, right?
we know the volts and we know the resistance.
Oh, okay. What's the resistance?
You see that? Can you see it?
Yeah.
16.46. What we did, here's what we did, Victor, a while ago before you got in. We took this information, we took the 3,500 watt and the 240 volt that's rated here. We took that. And we said, we took the numbers there of.
What is the resistance again?
16.46 ohms. And I'm just showing you where we come up with that because you just stepped in here. Look at here. We took the 3,500 watts here. And then we took the voltage of the 240. You see that? We covered up I, and it said P over E gives us I. All right, and they came up with 14.58 amps. And then I asked them, I said, if I'm troubleshooting it, what would be the resistance in ohms? What would be the ohms of this? And then they told me that they would use this formula, E over I. So the E would be the 240 volt, and the I that they calculated was the 14.58 amps.
Well, the other one is going to pull 12.63. Okay.
Okay, now look here. The R, when we covered up the R, it was E over I equals R, right? When you divide, and then they came up with 16.46 ohms. Everybody agree with that? Now, so my question now would be, with the same exact heater element, assuming that the resistance is going to stay the same, and it'll be extremely close. It may vary a little bit, but it won't vary much at all, very little. Nothing like a light bulb. A light bulb is drastic, a drastic on change in resistance because of a tungsten element in there. The way it works, it's just a drastic change in resistance. So how did you calculate this amps here?
Divide your voltage by your resistance.
Right. So we said here, I'm gonna get rid of this, and it really helps me a lot if I actually plug numbers into the triangles. So we're taking the 240 volt, and we're gonna reduce it. So 208 volt over the same resistance. We had the same heater element, but at a reduced voltage. And I say, what is I? I cover that up, and then what does it equal?
12.6.
12.6. And then what's the unit of that? 12.6 what?
6.3.
Oh, 6.3?
Yeah.
12.63 what?
6.
What's the unit?
6.
What's the unit though?
Amps.
Oh, amps.
Amps. Right. Now, does that seem reasonable that when we reduce the voltage with a resistance that stays the same, okay, when you bring the voltage down, that the answer to the equation would have to be less, wouldn't it?
Yeah, because if you go lower in your voltage, your amps are gonna be higher.
Well, here, when the resistance stays the same, but yet your top number changes from 240 and it goes down to 208 volt, it's a smaller number that you're dividing into, or saying 208 divided by that same number. The answer has to go down, right?
Yeah. My bad. I looked at it wrong.
Right. When it's a fixed resistance,
Yeah.
if it's a fixed resistance, we're talking a purely resistive load here that's pretty rock solid when you change voltage going to it. So as the voltage goes down with a fixed resistance, then the amps are going to go down. All right. So now, how do we arrive at and then we would want to say at 208, what would the watts be? There's a couple of ways you can calculate that.
Multiply your amps and your voltage.
Right, exactly. You can take the amps and the voltage right there, and you can plug them in there. There's a couple of ways of doing it. There's more than one way to do this. Can y'all see my pad pretty good what I'm writing here?
Yes, sir.
208, and then the amps that we calculated was what? I didn't even write it down. Well, I did write down. I wrote down on here. 12.63 amps is what you had. So if you multiply those, if I'm searching for wattage, I put my thumb over this, right? I cover it up, and when the letters are side by side, you multiply. Everybody got that?
Mm-hmm.
When the unknown is on top, then and they're side by side, it's multiplication. If the unknown is here, this is division. If the unknown is E, then it's division here. And the triangles are really great for cover up the unknown, and the formula just comes right out at you, So what do you come up with here?
208.
How much?
What was the amps?
12.63.
2,627.
2,627.
Yeah.
Watts.
Mm-hmm.
And let's just see how close that is to what's actually stamped on there. They're rating it at 2,500. They're rating it kind of conservative there. If that's a 5, and I think that is a 5. It's kind of scratchy looking. It looks like a 5, but it might be a 6. Now I'm not sure because it's kind of scratchy looking. It may be a 6. But no, it looks like a 5 to me. For some reason they're giving you the 2,500, and there may be what may be in account here is you may have a slight change in resistance in there that they are accounting for. It may be a slight change, and that would have to be the only answer to a difference between the 2627 and that 25 there, is that there may be a slight change in that resistance, but it won't be much. But you see you're in the ballpark there. You see there, you're kind of in the ballpark. You are in the ballpark there. But they're evidently they're evidently see a little bit of drift in the resistance of it whenever they go down in voltage, but not much, not drastically like a light bulb. Okay. So anyway, that's as close as you can get it right there without actually. The way you would know for sure would be to actually put 208 on here and measure the amps. Measure the amps, and then you could actually use the real amp draw to calculate the real ohms at that lower voltage. You could do that, and that would be a way to really verify this. You know what I mean? And another way to verify that wattage would be when you got it wired up and you got 208 applied to it. With 208 applied to it, you could take your amp probe and put an amp clamp around one wire here, one of these leads, measure the amps. And when you get the amps on there, then you could go up here and take the actual measured amps, plug it into here with the actual measured volts, and see what do you actually come up with on the real power consumption, you know, and just see how much closer it is to this. You know what I'm saying? You could do that to verify and see, you know, why there's a little bit of difference here, and figure out where that is. The difference has to come in. It has to come in with some variation here, a little bit of variation, but not much. So that's the only thing that can mean, you know, because Ohm's law itself, if you really did have it dead solid here and it changed none, then your numbers would be dead on. They would have to be dead on. These formulas, they never lie. When there's a variation between a calculation and some stamped number, then there's a reason. There's a real solid reason for it, and it has to be R. It has to be R in some small amount changing there a little bit. But on our paperwork, we're just going to assume it's the same so you can understand the formulas better, you know, okay? But bottom line, you know, your first calculations, if you were running if you were actually running it at 240, then that it would have to be close to that number of amps whenever you check amps, you know, around one of these leads. It would have to be close to that. And then that resistance, when you check it unwired, it would have to be close to that. And it can vary some, you know, in real life, you know, this one, when we checked the resistance, you know, we didn't get exactly 16.46. And the reason that you may not get exactly that when you measure it is because of something called tolerance. Now, resistors and heater elements have a tolerance. And it can be plus and minus some percent, like maybe 10%. And it doesn't give you a tolerance stamping on here, but all resistors, all loads have some tolerance. And it might be 5%, 2%, 1%, and some things can be 20% on tolerance of a rated number of ohms. Okay. And so, and I'll show you something about tolerance in a little bit. We're not there yet. But anything that's manufactured is not guaranteed to be perfect. There can be some leeway whenever they make the resistance element in there. And what they'll do is whenever they make a batch of these, you know, thousands of them, they'll measure them, and whatever the variation is, they'll put it in terms of a percent. And then you have to know that even though, you know, on paper it's supposed to be 16.46 ohms, then it may be 10% less, 10% more because of variations in their manufacturing process. You know, you can have some of that. And if it does, it would actually change. That wattage consumption would also change if with some tolerance there. So you do have leeway with everything in reality. Okay. So any questions about what we just calculated there?
No.
Okay. I'm going to plug, you know, your numbers in If this was rock solid, then your numbers would be dead on, okay? Your amps was 12.63 and your wattage was 27 watts. The math is perfect if that stayed perfect, okay? And I'll just say that, and I know that for a fact, okay? Now, has anybody had any problem doing their worksheet for chapter 2? Those of you that have had time to get on it.
No, sir.
Okay. So now we start our series chapter. We'll switch screens. And what we're talking about with Ohm's law, it's going to apply to a larger circuit now. Okay. So for series circuits, this is chapter 3, and I have not put chapter 3 in Moodle as far as a copy. How many of you, does everybody have the book now? Does anybody not have the textbook?
Not me. I still have to get it.
Is that Victor?
Yes, sir.
What I'll do is I'll scan a copy of chapter 3 and put it in Moodle. I don't have it in there yet, but normally by now, if everybody's got a book, then I quit putting scans of the book in there. You know, but I'll make a note for tomorrow. And I'm making a note to actually email you the chapter copy too, directly, okay? So I'll do that tomorrow. And I'll put it in Moodle for anybody else because we're missing a lot of people in the class right now. And there's probably other ones that don't have it. Okay, now moving right along. We're going to look at the relationship between voltage, current, resistance in a series circuit and use Ohm's law to calculate unknown quantities. Now, there are 3 rules to series circuits, 3 rules. Your worksheet that I got to get it converted into Moodle. You know, I got the worksheet that's actually, you know, the real paper thing here. That's what I've got now. Everything I'm doing now, I've got to convert bit by bit into Moodle. I've never done this class with Moodle. So I've got it's my first go and it's going to take some time for me to get everything in there. But like question number 3 on the worksheet says state the 3 characteristics of series circuits. So you're going to have to state the rules, okay, in detail. So here's the first one. The first one says this, that the sum of the voltage drops across the individual resistors or heater elements or light bulbs is equal to the total applied voltage, which means this. Here they have 3 light bulbs in series. And when we say series, here's what it means as compared to parallel. A series circuit means this, that we leave the power source and we go to 1 light bulb, okay? Here they got a battery here, a DC battery. That symbol, by the way, is a DC power source that can be a flashlight battery, a car battery, or any kind of battery, okay? So here they're leaving the minus terminal here, and they go to the first. These are DC bulbs like on a vehicle. So they would be typically like 12 volts, something like that, if it was a car. And but you don't hook them up in cars like this. But you go from the power source to the first light bulb. And then you leave the second light bulb, and instead of going back to the power source like you did in your first lab there, you're going to leave the first light bulb and go directly into the second bulb. And then you're going to leave the second bulb and let it go into the third bulb. And leave the third bulb and go back to the power source. And then you have actually one path of current that goes through all three bulbs. The same number of amps flows through all of them because there's only one path of current, okay? Now, some things you hook up like this, some things you don't. You're just going to learn. We're learning the rules of series, and then we go to parallel, and they all have characteristics because you'll find out in industry that you have all of it. You have series, parallel, and you have combination of both in industrial particularly. So this rule here that says ET means E total, with a subscript of T means the total voltage, which would be, you know, the voltage of that power supply. If it was 12 volts, for instance, then E total would be 12 volts. Everybody got that? Everybody with me?
Yes, sir.
E total would be equal to the voltage drop E1, which would be the voltage drop across the first light bulb. E2 is the voltage drop across the next light bulb. If you put a voltmeter lead across the second bulb, you put the meter across the first bulb, that will be E1 showing up on the voltmeter. You move to the second bulb, put it across there, it's going to be, the voltage drop would be E2 across the second device. You move your leads to the third one, across the third one, it's called E3. And then the dotted lines means that you could have more things in series, and EN means the N would be however many of them that you have. It's an unknown. It could be a bunch of them, you know. So in a nutshell, if this was 12 volts and all of these light bulbs were the same exact type of bulb with the same resistance in them, here's what it would mean. The 12 volts would be divided evenly among those three bulbs, and you would have 1/3 of the voltage across this bulb, 1/3 of the voltage across this one, another third across the third one. So how many volts would you measure across lamp number 1 in this case if it was a 12-volt battery? A 12-volt battery, and you have 3 light bulbs of equal resistance. And each bulb is going to give a voltage drop of 1/3 of that 12. So what's 1/3 of 12?
4.
4. Exactly. So if you put a voltmeter across lamp 1, it's going to read 4 volts or very close to it. There'll be some tolerance to that because the resistance of them bulbs ain't going to be, it's not going to be identical. I doubt it. There is a tolerance there. So, you know, you can see it's going to be pretty close. And then if you read voltage across the second bulb, what would it be? How much voltage would you measure across across lamp number 2? How many volts do you think you would measure?
4.
Right. And across lamp number 3, what do you think you would get? It's kind of breaking up. Can you say it again?
4 volts.
4, exactly. You would read 4 volts, 4 volts, and 4 volts. And those voltage drops, each time it goes through one of the lamps, the voltage drops again. So each one is actually dropping 4 volts. The next one drops another 4. The next one drops another 4. And that accounts for 12 volts. Okay, so that is rule number 1. Rule number 1 says that the sum of the voltage drops across the individual resistors in a series circuit, when you add them up, they equal the total applied voltage of the power source. Okay, everybody got that?
Yes.
Now let's actually see that. Let's just see that on a basic proto board I have over here. I'm gonna cut screen share off and go to the webcam, and I've got a small little board here that we're going to use as an example. I've got some resistors here that we're going to use. And before we do that, I'm going to show you that I got the contrast fixed on this oscilloscope to where I can make it nice and clear for you. I'll take 1 second to show you that. Just go. You see how much clearer that is now than what it was the other day?
Yes, way clearer.
The contrast, when I press F4 for contrast, and then I hold the up key, I've got to actually hold it in, it's going to get darker. You see it getting darker?
Yes, sir.
And then if I hit the minus key, it's going to lighten up on it to the point where you're not going to be able to read it. You see how light it got? And the contrast between the two, now you can't read it on a video camera. So I'm holding the up key, and you just got to hold it in for it to change. And so it got nice and sharp there. Now I'm going to show you here. I'm going to probe. Hold on. I'm going to probe the output of that frequency generator. So I've got some test leads right here coming from a function generator. I'm going to cut it on and go up. And so right now on the frequency generator, let's switch this over that I can read hertz and volts. It's got a dual display. Right now I'm reading AC volts up here and then DC on a dual display. So it's telling me, do I have any AC or DC on the line? And let's change, if I change the units here, I can hit here and then go way over here and hit hertz. Can y'all see it pretty clear?
Not really.
How about now? HZ for hertz. Can you see that?
Yes, sir.
So when I go across on the menu and I change that, I back up that. I want you to see what I'm doing. When I use these keys and I go across like that across the menu, and I get the hertz and I hit the enter, then it actually changes the display to read hertz up here, frequency, and then the AC voltage is in the second display. You see that pretty good now? Y'all see that? Now I'm going to vary the frequency. We're sitting at about 60 hertz right now. I'm going to vary it and change it. When I raise the frequency right there, you see the waves actually compress. So you get more cycles per second at a higher frequency at 87 hertz. You see it actually compress in. So if I go, now watch this. As I change the frequency, you're going to see it actually be like a spring that compresses. All right, so watch it good. There's more cycles per second now. Do you see that? Can y'all make that out good?
Yep.
If I lower the frequency, there's not so many per second. You get around 60, that's what we got coming from the power company. Now, what if I go lower than that, like slowing a motor down? Look at here. Then there's less per second. Then it gets elongated like stretching a spring. You see that? So that would make a motor go way slower. That's what we do in motor controls, is we actually slow the frequency down, and it makes the motor slow down. So when y'all take motor controls in January, we'll get this out and let you see how it looks when you change frequency. Okay. So let's cut this off. Let's get to our series thing here, because our time is slowly going away. Now we'll go back to here. Cut that off. Now our series circuit is this. I have 3 resistors in here that are 100 ohms a piece, and I sent you a thing on color code. I just emailed it to you. Now, right now, for the sake of time, I'm not going to explain the colors, but I will talk about it when I see you Tuesday in person, and you can read on it. But those color bands mean 100 ohm, and that silver means it's a tolerance of 10%. I've got one resistor here. I've got it in series with the next one, in series with the next one. So here, if I put voltage across here, 12 volts, I should read about 4 volts across each one of those, okay? It'll be a little bit of a tolerance there, but it'll be close to it. So I'm going to take and put my power source right there, coming from V1, and then I'm going to leave there and go back up to here. I'm going to put a plus. I'm going to put 12 volts on the connector right here. 12 volts plus, and then I put the common right there. And we have a series circuit. Do y'all agree it's series?
Yep.
You got one path all the way through, and then it goes back to the negative on the power supply. So let's move this up right here. And now, where's my test leads at? Here. I have a DC power supply over here that's adjustable. It goes from 0 to about 30 volts or so. I plug into the plus. It's going to go up here to the plus on the board. So I've got the DC power supply there going into the plus, and then I'm going to take the common. My common black wire is not long enough. I'm just going to use another red one to do that, to get enough length. I didn't get a long black wire out of the other room. So they'll both be red, even though they would not normally be. And then we put our common negative right there. So I've got the DC power supply. I'm gonna go up with it to 12 volts, very slowly, and let you see that. Let's go up. There's a fine and a course adjustment there. You see the word fine and then the word course down there. I'm going to do the course adjustment. And go up to 12 volts. It's at 12.1. I can use the fine adjustment to bring it back to exactly 12. And now it's dead on. So I've got 12 volts DC coming out of the power supply, going to the circuit, okay? So you see the 12 there, and let's raise this up that you can see the voltmeter when we do that. So let's go. Now on the meter, we have two kinds of voltage readings. Now which one do we go to? Do we go to the wave or to the straight line? And what do they mean?
I think the straight line is DC
It is DC.
and your wave is AC, so it's alternating.
Right. So here we got, what kind of power supply do we have here? It says what? AC or DC?
I can't see that. DC.
DC direct current. So it's not alternating. It's just steady DC. Okay. And we got 12 volts there coming from it. And we put our meter, we're going to put it on the DC volt setting. If you put it on AC, it's just not going to read it because there's no AC there, okay? Now, if I read across the first one, I'm getting 3.3 volts. You see that?
Yep.
Let's see what I'm getting across the whole circuit first, because through the jumpers, I may be losing a little bit. Hold on, let me get myself positioned where I can read better. I'm trying to hold too many things with my hand, and I've got this here tilted. Let's change the meter, the one that'll stand up by itself. So we're going to switch to that larger. What did I do with it? Right over here. Yeah, right here. Doing the camera thing is can be a little bit of a challenge, but just bear with me and we'll get it right here. So this meter here has a base on it that I can actually stand it up, so it'll stand up for me, and then I can concentrate on holding the leads. So just over with that, let the meter sit still like that. Now, and let's reposition ourselves like this. And we're going to go to volts DC. And let's get a better angle. All right, a better angle there like that. And now, I think you can see everything now, can't you?
Yep.
And I can hold everything now. So let's measure the voltage and see, are we actually getting 12 there? I'm not getting but 9 for some reason coming into this thing. Let's see what's going on here. Let's check it up here. I'm getting a backwards. If you hook the probes up backwards, it's going to give you a negative reading on there. That's 11.99 right there. 11.99. Let's fine tune and get it up at 12. Now, for some reason, in those little connections there, I'm losing some voltage there. So let's wiggle them a little bit, and then those quick connects, I'm losing some. Let's check it again. This proto board, you can lose voltage in there. Now I'm getting it now. You see it? 11.98. Let's actually fine tune it and get it on 12. So I'm going to bring it up a little bit at 12. Now we're getting 12 volts to our circuit now. Everybody see that? We're getting 12 volts entering the circuit here across the where it enters and where it leaves. You're getting the 12 volts. Well, we were getting it. So why are we not getting it now? These little jumper plugs here can be all right. Everybody see it? That's 12 volts. Now we're going to go across just the first one, the very first one. So I'm going to go from the entering into it and go right across that first one. And what do you see? 3.95.
Yeah.
Almost 4 volts. You see it? And you see where my probes are? I'm reading across that one resistor. Can y'all make that out?
Yes, sir.
Again, to get it closer, you're reading basically 4 volts across that one. Now let's go across the next one. We go across the next one. You see me going over here, and what do I have across it?
Same voltage.
Almost 4. Matter of fact, I can actually boost that voltage a little bit and make it be dead on. Okay. So if I hold my leads right there like that and turn the power supply up some, now I've got 4 volts on that one. I bet I got 4 volts on the top one now by giving a little more juice to it. You got 4 across the first one. There's 4 volts across the first one. Y'all see? Can you see what I'm doing?
Yeah.
And now I've got 4 volts across the next one. And now across the last one, I've got 4 volts. You see that, how it's equal? If I go back to what look at what happens here, guys. Look, I've got 12 volts there, 12.22. Now look, then I go, when I leave this one, it's actually 8 volts because look, I dropped 4 there. When we say we dropped in voltage, it's dropping from 12 right here. It starts out at 12, and if I move it over and I leave my comment at the end of the circuit, and I move over one place, it show me I've dropped it by 4 volts. Now I've got 8 volts left. That's like if I had $12 and I spent $4, I got $8 left, right?
Mm-hmm.
That's like money. When we say we drop voltage, that means I dropped $4. I spent $4 somewhere. So this one here consumed, it dropped 4 volts. So there's 8 left. You know, then I come, you know, there's 8. There's between these last 2, entering the second one, leaving the third one, there's 8 volts between those. There's 8 volts. Now, if I move at the bottom of the second one, it tells me what's left now. So the second one dropped another 4. You know, it dropped it from 12 to 8, 8 entering into here, and now there's only what leaving there 4, right? There's only 4 volts left for this last one. So the last one gets 4. The last one gets 4 volts as well. You see it? Everybody got it?
Yes, sir.
Yep.
It works this way if it's resistors or if it's heater elements. On a bigger scale, you got larger loads like heater elements or light bulbs. This is a small scale showing you with resistors the rules of series. So basically, look, if I measure across any 2 of them, if If I go across this one and that one right there, I'm getting 8 volts, right? If I go across the last two, it's 8 volts. So it's 4 plus 4 is 8, right? You got 8 there, which is 4 plus 4. But 4 plus 4 plus 4 is 12, right?
Yes, sir.
Now, so that's a close up of what I've got there. Is when you open your email and you get the color code chart out of there, you calculate what does it mean when you have a brown stripe and a black stripe and a brown. It's brown, black, brown with a tolerance of silver, which means 10%. But the brown means 1, the black means 0, and then the brown, the third one, is a multiplier that you multiply by 10. So if you have a 1 and a 0 and you multiply by 10, it means 100. And that chart, when you look at that chart, that's what it means. The first two are the first numbers, which would be a 1 and a 0. The third one is a multiplier. It tells you how many zeros to add. You add a 0 to the first two numbers, and that's something you can look at when you open your email at the color code chart. I'll show you briefly what I sent you. You see that chart there? Does everybody see that chart?
Yes, sir.
We have these resistors got four bands on them, and the first two are just simply numbers that you jot down. Brown is a 1, and then black, we have black for a second color band is a 0. So 1 and 0, that's like saying 10. And then the multiplier, we don't have this 5 bands like the one down here. So we don't use the third band here. We use a multiplier as the third band. And it means a brown would be a multiplier of 10 ohms. So you would take the first one, which is a 1, and then a 0 on the second one, and then a multiplier of 10, and it's 10 times 10, which will be 100. Okay? And then silver means 10% tolerance. When it's the third band, like here, or the fourth band here, the tolerance would be whatever color it is. If it's silver, plus or minus 10 ohms, 10%. Okay. So it's the nominal value is 100 ohms, and it could be 10% less or 10% more. It could be as low as 90 ohms. It could be as high as 110 ohms. So that's the tolerance on that resistor when it has a silver band on that third band there. And that's, again, when you look up closely at what I have here, and I go back to webcam, you see those colors there? You see the brown, black, brown, black, brown. That's 1, 0 times 10, and then silver means 10%. So these types of things is what you use on electronic boards, like in your computers. There's things like that in there. That's series and that's parallel. Parallel is a different chapter. Now I know it's technically time to go. Let me explain the other two rules real quick, if you got a second, and then I'll close. So going back to the chapter there. When you have a power supply of 6 volts, they show 2 volts being dropped across each one. And to calculate the total current, here's how you do it. You add up the resistors. The resistors add directly in series, so it will be 4 ohms plus 4 ohms plus 4 ohms here. Now, which will give you a total of 12 ohms. So our total is 12 ohms. And the way you calculate the total current would be is you take the total voltage, which would be 6 volts, divided by the total resistance, which would be 12 ohms. And it's going to give you a total current of 0.5 amps, because 6 volts divided by 12 would be 0.5 with the Ohm's law chart. So when you look at the triangle at the bottom there, it's going to be E over R, you know, the E total over the R total is going to give you I, which would be a half an amp. Here's what we're talking about. The characteristic, the second characteristic of series would be the resistances, they add up to give you the R total, okay? And then the third characteristic would be the current or the amps that goes through the circuit is the same for every resistor or every heater element or bulb that you have in series. So this half an amp here is going to flow through R1, and it's the same half an amp going through all of them. They share the same amount of amps, but they split the voltages equally if they're equal resistance. If they are, then you have, you know, a voltage drop of 2, 2, and 2. It would give you 6 volts. Okay, is everybody okay with that? Everybody still with me?
Yes, sir.
Now, when the resistors are not equal, then the voltage drop will be proportional to the resistance. So the higher the resistance, when you have a 4 ohm and a 12 ohm, the 12 ohm will drop more voltage. It's going to be about 9 volt drop across that. And then the 4 ohm will drop only 3 volts. And the way you calculate that is like this, is you take the voltage of 12 volts, and then to get the total current, you divide the 12 volts by the total resistance, which would be 4 plus 12 would be 16 ohms. The 12 volts divided by the 16 ohms give you 0.75 amps, okay? Now, to calculate the voltage drop across each one, you take the amps times the resistance, and it's going to give you the voltage drop across each one, because look, I times R equals E, right? If you don't know what E is, you cover up E. I times R equals E on top. So here's how you calculate those different voltage drops, is you take the I total that's the same in the whole circuit for both of these, which would be 0.75 amps, and it's I times R, right? I times R. You take that I, 0.75, times 4 ohms, and that equals 3 volts. You take the 0.75 amps here, you multiply it by 12 ohms, and it gives you 9 for 9 volts. And that's how you can calculate the voltage drop when you're doing it on paper, like we're doing in the worksheets, okay? So that's how that works. That's a very large power resistor, wire wound. It has wire wrapped around ceramic type of a base, and they can be used on some really huge applications. Now, the rule on you have the same current through all devices is stated like this. So when you get to work, when I get the worksheet in Moodle over the weekend, and you try to explain the 3 rules of series circuits, your third rule is going to be this: the I total, like the 0.75 amps that was in this circuit right here, the 3/4 of an amp that goes through all of it, I total equals I1 equals I2. I1 is the current that goes through the first resistor. I2 is whatever current that goes to the second one. Now, all of the I's equal, so I total equals I1 equals I2 equals I whatever, because we know that 0.75 amps, it flows through both of those equally. I1 goes through this one, I2 goes through this, which is the same, okay? It's the exact same amps. Any questions?
No, sir.
Okay. And here they're waited to the last to tell you that the resistances add up. That's actually your third rule. The first rule was about voltage. The second one's about the current. The third one is about resistance. R total equals R1 plus R2 plus R3, and then however many R's you had in series, you add them all up directly, and it gives you R total. Okay. Now you can be reading. I'll put the PowerPoint. I'll put the book chapter in Moodle tomorrow sometime. I can't do it today. I won't have any time to do it. Actually, I can. I've got time to do it today. As soon as I finish this recording, while it's processed and I get it uploaded to YouTube, I'm going to go right then and go ahead and scan chapter 3 and upload it in Moodle, and I'll email it. Victor, I'll email it to you. Roger, do you need it too, or do you have the book? I can just flat out email it to everybody. I'll just do a group email and everybody's got it. And that way I won't have to ask anybody, okay? But there's other things we're going to discuss, and I'm not going to hold you over. But those are the 3 rules. When you see that, that's the third rule, second rule, and first rule, okay? You can actually draw it out in formula form instead of putting it in words, okay? It's fine. E total equals E1 plus E2, so on. You can actually do it that way when you type it in Moodle, and that's going to make it simple. Now, I will explain this since you're hanging on with me, and that will complete this chapter as far as the lecture. And I will help you with the worksheet. Tuesday when you come, if you got questions, you're going to be wiring your bulbs up Tuesday like this. You're going to be putting them in series. Not that you would, but you could, and you're gonna learn and see the brightness change and see it get dimmer. And the bulbs helps you learn these rules very well by doing it with light bulbs. So your light bulbs, you're gonna have 3 of those hooked up in series, and things are gonna change drastically on what you see. Now, here on troubleshooting, we can actually do this when you're here. We can do it. A short circuit is a circuit that basically takes a shortcut home. When you take a shortcut, you don't go the normal route, right? In an electric circuit, if I had a light bulb, and for some reason when I took that fixture and I put the fixture on the box to tighten the screws, and both wires touched each other, which can happen. If that happened, you would have a bypass around the bulb, and it would be what they call a short circuit. Okay, it didn't go through the filament there, but it actually bypassed and then came on back. And when it does it, the voltage source doesn't see a load out there. It sees a straight wire, and it's going to try, by there being no resistance out there, it's going to draw a lot of amps, and it's going to blow a fuse or trip a breaker or burn the wires up. So a short circuit has got very, very little resistance. It's going to try to draw high amount of amps, and it can, if you've got overcurrent protection in there, like a breaker or fuse, it's going to pop it immediately. If you didn't, it's going to melt the wires and damage the power supply. So that's called a short circuit. An open circuit would be where I have a wire break, okay? Now, an open circuit can happen when you have a broke wire, an open switch, even a burned open bulb. If the bulb actually burns open on the inside, you have an open circuit actually within the bulb. Now, here's a characteristic of an open circuit. Wherever the open is or broken connection, if you actually measure there where it says open and you put a voltmeter across the open connections there, you will actually read the power supply voltage. So if it was a 12-volt battery and you had a broken connection and you put the meter across those two, you would read 12 volts out there. That's something we can prove it by taking one of your light bulbs out and measuring in the socket, and you'll find out that you will read, if you have a connection here, but you remove the bulb, you will read the power supply voltage. As a matter of fact, on 3 of those right there, if you remove one of the elements, and you remove one of the heater elements or light bulbs out of there, go back and do your bulbs, if you screw one of the bulbs out, if you screw, and we're going to do this and let you see it. If I unscrew bulb number 3, Pennsylvania, I don't know nobody in Pennsylvania. If I unscrew one of the bulbs, when you wired up with 120 volt here, and I've got all of them good, and I've got one bulb just out, or either a blowed one, here's what's going to happen. None of the bulbs are going to light up. None of the bulbs light up. If you get one bulb blowed here in the series circuit, there will be 0 current flow. The amps will stop. And then what's going to happen is the first 2 bulbs, they're going to quit too. If this one here blows, they all go out because there's no way for the current to actually maintain a circuit, a closed circuit there. So if there's no amps flowing, all the bulbs go out. And if you actually put a voltmeter across this bulb here, you're going to read the main voltage actually right there. You're going to read close to it right there. And that sounds strange, but we're going to do it when you're here so you can see it, that it actually works that way. When there's no amps flowing through there, wherever the break is in the circuit, when you go across that break, you're going to read something very close to the main power supply voltage. And you have to really see it on the board to actually to really take it in and see that it really does work that way. And these 2 scenarios, you will need to answer. There's going to be a couple of questions in the worksheet about what I just explained. And for you to answer, you're really going to need to be here to see it on your board. And then you can answer that question on the worksheet. So there'll be a couple of questions. One particular question, you're going to need to see it in person, really to be convinced that that's the way it is, okay? And there'll be a lot of calculations in the worksheet, but what we've explained is going to get you started very well with it. It's going to give you some circuits like this. It'll give you a voltage. It's going to give you the resistors or heater elements. And then you're going to have to calculate E1, E2, E3. You'll calculate I total. And when you calculate, when you use a total voltage and add up your resistors, it's going to give you an R total. The E total and R total will let you get an I total. When you get an I total, use I total, multiply by each resistor individually. It'll give you the E1, the E2, and the E3. Okay, that makes sense? Y'all still with me?
Yes, sir.
Okay, I know I've run over, but I've actually said plenty about this chapter to get you started. I will help you with it through when you get here Tuesday. We're going to talk about it some more because you're going to be changing your circuits to series now. Okay, those of you that are done with the last lab, you're going to be going this route. Victor, I know you're going to be going that route now. Okay, and Roger, you may be. I don't know who's done what, but anyway, that's and there's other circuits that you're going to see other sample problems in there. And so let's stop this here now. So do you have any questions at this point? I know I've run over, but sorry about that. But I'm glad you stayed. So it's recording for anybody that had to get out. That's fine. I understand that other people have classes right after this one and they can't stay, and that's fine. But the good thing is once they get it in YouTube, they can go back and watch whatever they missed, or if they missed the whole thing, And if you go in through Moodle to click it, then you get credit for seeing it. If you go straight to YouTube, I can't document that anybody watched it. So do either one of you have any questions about the chapter, what we looked at?
No, sir.
Is
Not
it? Huh?
not right now.
I can't hear you.
I said not right now.
Good. Is it making sense what you're seeing? Is it making sense, both of you?
It's getting in there. I just have to see it a little bit more,
Right.
try to comprehend.
You're going to see it with the light bulbs, and the light bulbs is the best thing in the world you can actually understand this with, because it gives you a brightness effect change when you do them in series. You're going to see a third of the brightness you would normally see, and you're going to see the voltage change. So even though you would not going to hook light bulbs in series in a house, you just don't do that. It's honestly the best way to understand these rules, because you get the brightness change and you get the voltage change and you see what goes on. It really just helps us to understand these rules better. And then when you see bigger things in the industry, like where you are, when you look at series and you look at parallel and combination, you're going to remember these bulbs. You're going to remember what you saw and how simple it was. And it's going to help you understand bigger things. And that's just really the beauty of making it simple now. Helps you get the rules, and then you can interpret larger things, because you know really the fundamentals of how electricity works. When you complete this class here, it's a class that you really can't overlook it. I mean, if you overlook it, you're going to be missing large chunks of understanding electricity that this class provides. So thanks for watching, and I'm going to go ahead and hit stop, and I'll go ahead and do a scan of this chapter, and soon I'll do it real soon here, and I'll email it to everybody, so you'll actually see it in your inbox, and I'll put it in Moodle too, so it'll be in there permanent. So thanks for watching. Y'all have a nice. I'll see Victor. I'll see you tonight if you can make it. And
Yes, sir. I'll be there.
good, great. And Roger, you have a nice weekend, buddy. You've already had residential. Roger did real good on residential. Yeah, and he's working with a contractor on the weekends now, doing residential. So, yeah. All right, thanks guys, and have a blessed weekend. Thanks for watching. And you know, you can text me anytime you want to. Call both y'all know my hotline's on the weekend. I'm available. You know, so.
Yes, sir. Appreciate
Anyway,
that.
Thank you. And one of these days we're gonna sit down and get us a fish plate. Whenever y'all get time, and
Yeah.
you get that next raise out there somewhere. We're gonna figure out when we can go somewhere and get some fish. If it's sandpiper or Carolina fish fry, I don't care. Just as long as it's some good fish. We need to go get it. And
Yes, sir.
oh Lord, my camera. When I move something over here, it actually cuts it off. But anyway, but that good old fish will be some good brain food there, Victor and Roger. We need that in this electrical field. We need all the brain power we can get, guys. You know. So I'm planning on going after them tomorrow night. To go to sandpiper and reel them in with a fork. I got my fork ready. I'm gonna sharpen that fork up and go get them. So we'll see you later. See you at 6 o'clock, Victor.
All right.
Thank you for watching. Y'all have a blessed weekend. See you in.